Okay, so hopefully I had that up on the screen to where it will show as the first screen of my recording. So anything good happen to you guys this week? Let's start off there before we jump into our topic.
I'm a federal project manager level 1. Finished the last course.
Very nice.
Yesterday.
Very nice. Yeah. The other thing that they say is very helpful for us is to learn the acquisition side, so that you can manage stuff with money in the federal government.
Actually, Scotty, I have a better thing. I can now translate to the customer what's going on in the background in acquisitions, and translating it to making sure the customer knows why something is taking so long to go through the process of paying for it.
Yeah, very smart. Yep, cool. Nerman, anything big go on with you this week?
No, nothing really new. I mean, same thing, studying, spending time with family, and yeah, that's it, I guess.
So you're working on your degree, right?
Yeah.
How far along are you?
Well, I have two more semesters.
Okay.
Yeah, and I will be done with my undergraduate program, and then I will start doing my master degree in the same field. Yeah.
Master's in what?
Information technologies. It's going to be related to my my major, cybersecurity.
Okay. The reason I'm asking is I read a very interesting article and very quickly just sort of caught it and moved on. But people with master's degrees in cybersecurity are an extremely rare breed and are really expensive when you go to hire them. I started to notice a master's degree in cybersecurity is one of those things that if somebody's on a track to achieve that, their pay will reflect it. But masters in information systems, masters in computer science, those sorts of things, people are getting those by the thousands. But the masters in cybersecurity is still, very few colleges that I know of are offering that, and very few people are graduating with that. Part of the main reason is, and I don't know if you are aware of this in the educational realm, in order to teach to a particular level of degree, let's say to a bachelor's degree, an undergraduate degree, your instructor has to be at least one degree level above that.
Yeah.
So in order to teach to a bachelor's degree, your teacher has to be a master's degree person.
Yeah.
So yeah. So to get a master's degree in cybersecurity, it has to be taught by somebody with a PhD in cybersecurity.
Yeah. I'm actually very lucky. Like most of my professors, they have PhD in the same field. So yeah.
Yep, very good. Okay. Well, good luck. We're here to help in whatever way we can. My undergraduate degree is in computer information systems, and I got that way back in, I'm dating myself, 1993, back when, computers were big monster things, you could barely carry down the hallway. A laptop, I can remember traveling, here we go, I'm dating myself again. I remember traveling with the Air Force in the 1980s, and we had laptops, and our laptop weighed 30 pounds because, it even had the monitor attached. You'd unbuckle the monitor and swing it up and then pull the keyboard down. So it was a great big monstrous steel case in which was a, like an IBM 80286 computer, and then you had the monitor and the keyboard, both of which, went inside the box. And that thing weighed, I think it was 32 pounds, and we still carried it on the airplane with us in order to do work, because we were developing training for a 100, I think it ended up being $155 million Air Force program computer system. This was just the programming language. The application that was being built cost $155 million, I think. But it was used for seismic monitoring and correlation, and figuring out where something originated, triangulation, and those sorts of things. And it was all being done by computers. Before that, it was being done by room-sized IBM 360s, literally the size of like my house here. Back in the 70s, the same computers that we used for seismic analysis, the exact same computers were also being used to calculate space trajectories for NASA. We used the same computers. There was one building in Florida, and at one end was the seismic computer, IBM 360, and at the other end was the NASA computer that they used for range calculations for, how much fuel do we need to put into this rocket type stuff. Really interesting. Two computers, same type of computers at two ends of the same building. So one end of the building was Air Force, the other was NASA. And, you wonder, why would the Air Force be involved in something having to do with ground tremors? Well, there's one thing man makes that's big enough to generate seismic tremors that can be heard all around the world. And that is a nuclear detonation. So that's why the Air Force was involved, because they wanted to hear this stuff anywhere around the world. So anyway, that's my history. I go back, way back. Yeah, Chris.
You said nuclear detonations. I went smaller and said fracking, oil fracking.
Yeah, but
that's smaller tremors, though, not big tremors like a nuclear detonation. Sorry, I digress.
That's all right. The military, though, is not that concerned with fracking unless it, destabilizes a geographic area or something, like underneath a NORAD or something like that. That would make a big difference. But no, this was for the U.S., a whole bunch of countries, many countries, signed a number of nuclear treaties. And they said, number one, that everybody was going to test underground. Why? Because when they tested above ground, this nuclear radiation stayed in the atmosphere and just sort of basically built up, sort of like lead paint. Remember the discussion about lead paint? You could get lead poisoning and it wouldn't hurt you, but if you continued to get lead intake for years and years and years, you could end up having kids with developmental disabilities. So that's why they stopped lead-based paint. Well, the same thing was occurring in the 50s and 60s in relation to background radiation levels worldwide. So, somebody started to figure it out and say, you know what, if we don't stop this, we're going to be in trouble in a couple of years. So all of the countries agreed to test underground to where their detonations did not vent into the atmosphere. And then there was something called the Threshold Test Ban Treaty, I think it was in 1974, which said that we would not, also that we would not test in space. That was another one. But also that we would only test a certain size device. So how do you verify that somebody is doing what they said in the treaty? You have to be able to verify the treaty. And the only way to do that is to have seismic sensors that go, oh, that was bigger than it's supposed to be, you know, from 3,000, 6,000 miles away. And so that's how seismic analysis became a tool of what was called the Atomic Energy Detection System, AEDS. And the Air Force was leading that. So anyway, old stuff. So I was using computers. Admittedly, they were room-sized computers, 1 megabyte of RAM. Big stuff. Back in 1977. Anyway, so I wanted to talk a little bit about quantum. Big word, and it leads you off a really large cliff into all sorts of other things. But Nerman, tell me your understanding of quantum computing, quantum cryptography, quantum anything that you've heard.
So yeah, I just read the article that you posted on Facebook, and yeah, they're talking about, so basically those are like faster computers, like more computing power and speed. So they're like capable of doing a huge amount of calculation in complex algorithms, and this means that let's say bad guys will be able, with this new advanced technology, to kind of like break the system. Like, so they will be able to their like hacking skills will be improved, and they will be able to breach the data. And so I guess now like people trying to develop something like quantum cryptography, like that will be at the same level of those fast computers,
right?
To protect the data. That's how I understood. So
I think you're spot on. If you are studying for something like your Security Plus, I don't think quantum is even in the security guide. I don't think the study guide. Let me look.
I don't think.
Yeah, quantum computing, page 222.
Oh, they have.
Yeah, let me see what they say about it. Yeah, there it is. Quantum computing, 2 paragraphs. So, emerging field, they say an emerging field, attempts to use quantum mechanics to perform computing and communication tasks, mostly a theoretical field. Well, we'll learn a little bit more about that, to where we can't really say it's theoretical anymore. And yeah, it talks about quantum cryptography may be able to defeat cryptographic algorithms that depend on factoring large prime numbers. And this says we'll have to wait and see how this affects. Well, no, we're not waiting to see. We're not. And the Homeland Security announcement, as well as the bill that was passed in the House of Representatives, point out that big money is being spent or is about to be spent to help make sure that we don't end up on the receiving side of quantum problems. So, yeah, very good. Chris, anything that you want to talk about before I go to the slides?
I just started my research on it this morning, so a lot of basic building blocks and just gathering resources at this time.
Okay.
But I put them up on Facebook if people want to see them, what I've gathered so far.
Super. Excellent. So this is what I have been able to assemble, and again, I was talking with Chris about this before we began. We've got to keep this at the gee whiz level, you know, wow, instead of I need to know that. You know, this is, I'm just trying to get you to expand your minds a little bit, because if you walk into a room as a cyber specialist and you have a command of quantum cryptography, as well as current methods that are being spent to address that, you are ahead of anybody else who has just been learning and sticking with traditional cryptography. All right? Quantum cryptography, and we'll learn a little bit more about it. Sorry about that little light that keeps going back and forth. It's not a UFO. We've got an open window here, and a bird feeder is in the wind, and it's got a flat face. So the light is shining on the face of the bird feeder, and the bird feeder keeps moving. So you'll see this little light thing going back and forth here. Sorry about that. It's not a UFO. There it went. So the important thing for us to remember is that this is it's being worked, and it's going to change a number of the ways we do business. And we can already identify what needs to change. Okay? So that's why I wanted us to talk about this, because that helps you understand what you need to study, also where you need to put your thinking power. You know, if somebody says, well, let's talk about this guy, PIV cards. And they say, you know, PKI. Well, PKI must change. Things like AES encryption, and we'll talk about that in a minute, but single key, and I'm using my, key from my shed outside. Single key is different. This is two key, so this is called asymmetric, and we'll talk about that. So anyway, first thing, cryptography. Let's get a basic understanding of that. It says it's the practice and study of techniques for secure communication in the presence of adversarial behavior. I think about cryptography this way. My secret stays secret. If you think about it. It could be something that I want to have, and also perhaps to communicate to the right people, and yet other people won't be able to know what we're saying. Okay, that's a way to think about it. We talk about the CIA Triad. Always, if you don't know the CIA Triad, you will not pass your Security Plus exam. Serious. Everything is based on that. So, Chris, you and I can both attest to this. When you go to a job interview for a 2210 position, any 2210, let alone a cybersecurity one, they talk about the CIA Triad. Confidentiality, integrity, and availability. Why? Because if you don't understand that, you could be applying work towards something that will not protect you. Okay? So you've got to be thinking about this, and stuff you do here may be inconsequential over here. You have to do stuff here. So the CIA Triad is confidentiality, integrity, and availability. Nerman, did you raise your hand? Okay, all right. And cryptography is, and Nerman, I'm going to ask you to answer, cryptography deals with which side of the CIA Triad? Which side? Your secret stays secret. Let's think about that one.
If I'm not wrong, like with confidentiality.
Yep, that's correct. Confidentiality. Sorry, you're going to have to learn that word. Confidentiality.
Yeah,
it's not like supercalifragilistic, where you don't need to know it. Okay, so it affects it deals with the C of the CIA Triad. Okay, it sort of deals with I as well when you talk about electronic signing and certificates, but we'll get to that. All right. So there are basically two approaches, and yes, this is in the Security Plus. So I'm not teaching magic tricks here. This is something that you need to be practiced in and understand in order to be successful in the cybersecurity career field. So there are two main types of what are called algorithms. One is called a symmetric algorithm and one is called an asymmetric algorithm. And it's based on what's called the keys for that particular algorithm. So I give an example of symmetric is like the key to your house. If you need someone to come feed your goldfish while you're on vacation, you give them the key to your house. And no other key, it doesn't matter what they have or who walks by and puts something in the door and tries to make it turn, it won't work. The point of symmetric cryptography is that the same key is used both to encrypt and to decrypt the information. So I'm using the example of a house key because nothing except this should work to get you into your house. Of course, people with their little hacker toolkits and stuff. But what I'm talking about is in order to open my front door, it takes a key. And it doesn't take any key. It's a specifically designed key. So that's called symmetric cryptography. And we'll talk about who uses symmetric versus asymmetric, but it's basically the same key is used to encrypt and to decrypt. Now, can you tell me what you think may be the problem with that? The problem with symmetric cryptography. Any ideas? Okay.
If anybody has the key, they have keys to the whole thing.
That's right. Once the key is divulged, you no longer have control of it. If I have my key to my shed and I know that, this is the only key to the shed, and if I keep it in the house, nobody's getting into my shed. All right? But as soon as I hand it to somebody and they just happen to wander by Ace Hardware and bzz, 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 now they have a key. Okay, so that's the problem with symmetric cryptography, is that once the key is divulged, your cipher is basically useless. Basically useless. Now, asymmetric, I tried to come up with a graphic way of describing asymmetric cryptography that didn't deal with ones and zeros. But think about it this way. Chris, do you have any ideas? I mean, because I'm thinking of a cylinder, a tube, and you've got your, let's say, a ball that you're rolling through the tube, and by the time it gets to the end of the tube, it's different. It's a one-way cipher. Okay, asymmetric uses one-way ciphers. And there's one that goes from this way, and a key pair, in other words, a paired public key that goes from this way. Neither one can be used in place of the other, and they are one-way ciphers. In other words, I can't take, let's say I'm rolling my marble from here through here and it changes. I can't take another marble and roll it backwards through here and say, this is to reverse engineer. It's a one-way cipher. And one of the, when I think of one-way ciphers, I think of, for example, Active Directory. Active Directory uses one-way ciphers so that somebody calls you up and says, hey, can you tell me my password? The answer is no. I can't see your password. If I'm a Active Directory, even a schema admin, your password is not visible to me, even if I own the system. Okay, so that's one-way cryptography algorithms. But when you have a key pair, asymmetric, you design these two. These two are generated at the same time. One goes this way, one goes this way, if you think about it that way. One is called a private key. The private key is, and I'm going to use this as an example because this has my private key on it. You know, that's attached to me in the public key infrastructure for the federal government. All right. My private key is only in two places. Any thoughts on where? You know, number one, it's on this card, and number two, any ideas on where the private key might be kept?
An authentication server. This is the part I struggle with.
That's all right. When you talk, the important word is private. And that private means you don't get a hold of it. Okay, it's literally controlled by the design of the system to where it only exists on a card that nobody can read, by the way. You can't read this card. This card, again, has that one-way algorithm in it to where my private key can be used, but it can't be viewed. All right, that's how this card is designed. The other place where my private key is stored is in the, what's it called, baby? Where the private keys are stored. Okay, wherever the computer that generated the keys keeps a copy. I know, it's in my head too. The computer that generates the key pairs keeps your private key and gives you your private key. Your private key exists nowhere else in the system. Nowhere. It's not on authentication servers. Yeah, my wife, she's literally telling me the system in which it's in, it's called the key recovery area, which uses those private keys. And the reason you have to have your private key over here, any ideas?
Scotty, is it a certificate authority?
So that's it, certificate authority. Yep, we're both pointing at each other.
Sorry, Google.
Yep, you're right. You're right. The CA that generates these keeps a copy. Why? What happens if my card gets lost or stolen? The CA has to generate a new card with the same key. Yeah, and you can't do it. Now let me rephrase that. Microsoft has built-in PKI. You can generate public and private keys even down to a switch level or a computer level. Your computer can generate its own certificate. The issue is nobody's going to accept it. Oh, right. Right. You become the certificate authority and nobody trusts you. So, by the way, the other thing to think about if we're talking about PKI, public key infrastructure, it's known as a web of trust. And in order to use it, you have to agree to do things like keep those private keys secure. I remember in the Department of Defense, they had a CA workstation, the Certificate Authority Workstation, that had the capability to generate these keys. And by the way, it kept these keys. It was inside our comm center, locked in a specific room that, oh, by the way, you could only get to with a particular key, and those keys were controlled, you know, et cetera, et cetera. So the CA workstation was not on the network. and nobody could walk up to it and log in. So it was like protected by multiple layers of security, because if that CA was compromised, the entire DoD PKI would become compromised, and everybody would have to get new cards. 3 million new cards. How long would it take to generate those? So anyway, public key and private. Okay, baby. Public key and private key. My private key is on here. Where is my public key? And I'll make this fast. It doesn't matter where. It can be anywhere. If you have a Microsoft Exchange global address list, you can store public keys in that. We don't at our place, Chris, but you can. I've actually stored mine up there, but it's a manual process. If you are doing anything that has asymmetric cryptography, you must publish your public key in order for someone to send you something encrypted. Okay? They get a hold of your public key and they say, I want to send something to Scotty Ward. So they go out and they find Scotty Ward's public key, and I can send my public key to anybody. I'm dating, baby. Can you turn it down, please? Back in the day, people, if you remember, they used to have their email signature, and then underneath it was this big bunch of characters. Do you remember seeing any of those? It's been a few years. It was called the PGP public key. And the reason PGP was in use is that nobody owned it. It was open source. And therefore, privacy advocates said nobody can steal it. It's open source. So you can generate, using the PGP system, a public key and keep your private key private, and then people could send you encrypted email using your PGP public key. So long time ago, people published their emails. They said, "Hi, I'm Bob, and I'm working over here in whatever, and please talk to me." Signed Bob, and then down at the bottom you'd see this big monstrous thing that said PGP key. And that was in case we wanted to conduct encrypted conversations. And PGP, again, was open source. One thing to think about, anything that's out there can be used by the bad guys. Some of the stuff that goes on, it's called spread spectrum, but it's extremely difficult to listen into and eavesdrop on encrypted voice communications, and in many cases electronic communications, if they are being encrypted using methods that they don't have control of. So it's important to note that it's people who are trying to break asymmetric encryption are not always the bad guys, because bad guys use asymmetric encryption too. Bad guys, could have their own public key, private key pair, and we want to know where they're planting their next bomb or which plane they're planning to hijack. See what I'm saying? It's not a good guy, bad guy sort of thing. The technology is being used by both sides. So public-private, we'll talk about exactly what uses those, but then we get into quantum cryptography. Quantum cryptography, and this is just my saying to you, quantum cryptography is relatively ineffective against symmetric algorithms. It is highly effective against asymmetric algorithms. Okay? That's just something for you to think about. Symmetric algorithms, one example here is AES. AES encryption is symmetric. AES is in Active Directory and many other groups. They use AES 256. AES 256 is the minimum standard, I believe, Chris, for network encryption. I think AES 256 is considered to be the minimum standard. So, and by the way, it talks about it this way. It's either a 128 or a 256-bit long key. And by the way, remember that word bit? We're going to talk about that. Bits don't really make a translation over to quantum. Remember? We changed from a bit, which has two states, 1 and 0, to a qubit, which can have 3, and I didn't get into this in my post on Facebook, 3 or more states. 3 or more states. So, wow. So here are some asymmetric algorithms are being used for things like encrypting email. It's also used in your web browsers for SSL. But it also includes TLS. And TLS is used as part of the Microsoft security application layer. So Microsoft has to change. Browsers have to change. Our public encryption method that's used to move stuff around on the World Wide Web has to change. And then here's a scary one. See number 3? Cryptocurrencies use public-private keys, if you want to think about it. Asymmetric. So, imagine cracking Bitcoin. What will happen if somebody, and theoretically, remember that your crypto is, you may own your public or your private key for your crypto. And I don't know if you guys have done anything with crypto, but they say you're supposed to take your private key, put it on like a thumb drive, and never plug it in. Okay? Because it's only available one place, and that's your thumb drive. Your public key goes all over the place so that people can see and quantify and trade with, etc., various crypto. But imagine having a method to where you can, it's using the wrong word, but guess everybody's private keys. Do you know what it takes to own crypto? You transfer the private key. Think about that. If I were able to grab everybody's private keys, I would then own Bitcoin or whatever the crypto is. I would own everything. Wow. So that's going to be a big deal. Cryptocurrencies are, they're big, they're small. People are putting big money into them. What was it? This last year, Tesla said they would accept Bitcoin. Excuse me. If you wanted to buy a Tesla.
Yeah, Dogecoin. Dogecoin was the big last year.
Right. Well, I will tell you that Shiba Inu, and I'm only going to talk about that one. I put $200 into Shiba Inu. Why? Because at $200, I could buy about 6 million Shiba Inu coins. So if the Shiba Inu suddenly goes to 1, one coin is worth $1, I will have made, something like $6 million.
Yeah, if you put $200 like in Shiba Inu, like a couple of years ago, you could buy like I guess like like over like 100 million of those coins.
Right.
I remember I put like $20, 25 bucks, and I got like I think like 7-8 million.
Right. Right. Well, for what you did for 20, because you did it early, cost me 200.
Yeah.
But there, you know, I'm looking at the forecasts, and they say Shiba Inu could hit 1 by 2050. Okay, $7 million by 2050. I'll hold my Shiba Inu.
Yeah.
It may turn into nothing, but you know what? It may turn into something.
Yeah. I mean, 200 bucks, it's not a big deal, like, so keeping somewhere, like, so.
Right.
Not.
Right. So number 4 here is PKI. And what I mean by PKI is public key, private key, not only for, I said electronic signatures, but also encrypted email, the top one. That uses PKI. And all of those have to change because, and we're talking theory that is becoming real. Okay, we'll talk a little bit more about that, but I wanted to get into quantum computing and what's going on with that. We talked on Facebook, I showed you a diagram of a qubit. I'm not going to repeat that here, but basically remember that a bit has 2 states and only 2 states, and a qubit has 3 or more states. So it's like turning everything into a brand new way of thinking. They're starting with physicists to design quantum computing. Back in the day, they started with physicists before they came up with the idea of the transistor, which the transistor is being used today for our computer chips. CPUs use a micro mini group of what are known of as transistors. How many transistors can you fit on a chip? And that's the other thing we have to think about. And I'll talk about this. So it talks about quantum states, superposition, interference, entanglement, blah, 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 blah. Way too big for me. Way past what I'm coming up with. The issue is they're now combining computer science and quantum physics together, and everything that we're thinking about is going to have to change. Yes, normal bits and bytes will still work, but if you want them to remain confidential, they may not. And I did hear somebody is theorizing about what's called quantum internet. If you can do it on a computer, you can do it on a switch. Imagine. So way down the road here. So is it new? Is it theoretical? No, it's not. In 2019, that's 3 years ago, IBM released a quantum computer that they called the Q System 1. And here was their, if you look at their marketing, had a 27 qubit Falcon processor, and you can upgrade to their 65 qubit Hummingbird processor or their 127 qubit Eagle processor when they become available in late 2023. Okay? So the big thing, if you remember, we used to talk about transistors on a chip. Now they're talking about qubits that you can access. D-Wave Systems, however, had a 128 qubit system that they sold in 2011. Guess who their number one client was? Any ideas on who D-Wave sold their first computer to?
Department of Defense would be my first guess.
It was a Department of Defense contractor, Lockheed Martin. And just so you know, the D-Wave 1, the D-Wave 2, I think it's the D-Wave 2000Q and the Advantage, when it comes out, Lockheed Martin owns one of each. We're not just talking one, we're talking every time they come up with new ones, somebody, I'll bet you it's, federal, gives Lockheed Martin the money to go buy these things. NSA is heavily investing in this because, remember, good guys, bad guys, if the bad guys, or let's say a nation state that doesn't care who they sell to, let's think about it that way, like China, if they sell to, I don't know, a rich Saudi oil prince who happens to be buddies with the guys in Afghanistan or North Korea or, who knows, Russia, NSA has to be able to address and annul that threat. So that's why, if you take a look at it, by 2023, 2024, they're saying, and I'll bet you COVID has slowed this down towards 2024 now, their newest computer system by D-Wave is supposed to have over 7,000 qubits. And if you remember, IBM in 2019, they had the Q System 1 that had 27 qubits. And now they're talking 7,000 qubits within the next couple years. Okay? That's a big deal. The thing that we have to remember, and I'm going to go to, by the way, it's a Canadian company. Go Canada. You rock. That's great. Canada's our pal. So these are all superconducting semiconductor computers. All right? So they use traditional silicon CPUs. Silicon, or a variant thereof. Superconducting semiconductors. Google, in 2019, they declared that they were, top of the heap with a 53 qubit processor. However, and again, this is the difference between theoretical and actually doing something with it. Okay? Theory can be accomplished in a lab, but to then say, go crack, the Department of Defense's PKI, it takes a while to develop that. But they say Google is hoping to develop a useful error-corrected quantum computer by the end of this decade. Now, that's another thing that I sort of talked about. With all of these quantum states, the issue is we're not talking a number 1 or 0. We're basically talking about positioning of the qubit in an atom, by the way. So the issue is this qubit can be wrong. It has a high chance of being right, but the qubit state, when it's used for calculation in an algorithm that could be used for asymmetric cryptography, can have errors. So that's why Google is talking about an error-corrected quantum computer. All of these others, they're doing theoretical, and they don't care about the errors. And in fact, there was an example, I think I've got it on one of these other ones. No, I'll talk about the Chinese in a minute. They had, I think it was a 66 qubit processor, but because of what they were doing, they ended up only using 55, or it was 63 qubits, they only used 55 qubits. Why? Because the other ones probably had errors at the time they were doing their algorithm. So they're sort of like, let's use these, because these worked. But here's the thing, and this is why I say the Chinese are ahead of the game. The Chinese are doing their qubits optically instead of using superconductors. They're doing it using light. So they're talking about photons versus little bits and bytes going across a line inside of a matrix that is built of something in a supercomputer. You guys have you heard about the size issue with computers and why chips were a certain size and now they're down smaller, but they can only get so small? Do you know why? Okay, superconducting supercomputers have the smallest run sizes, but they still have runs. They still have to design these runs and stamp them into chips, and so they have mass. The issue is they get down to a certain size, and I think they said 5 nanometers is the smallest they've gotten, nanometers, so itty bitty 5 nanometer run. When they try and go smaller, what happens is the bit jumps from one run to another instead of following the run. So therefore your computer processor doesn't work. So the deal is they're using electricity, and electricity can jump, it can short if you have your two conductors too close to each other. Remember all the science fiction stuff where they put these two things together and they go bzzz. That's what happens in your supercomputer if your runs are too small and too close together. Okay, so they're talking about a theoretical size limit beyond which you can't shrink chips, because electricity will start jumping between the runs, and therefore it stops working immediately. So that's the problem with these superconducting supercomputers. So they have a theoretical limit that massless light, again theoretically, light has no mass. If you can figure out a way to split light into enough spaces on an emitter and a receiver, everything in between will never touch itself, never touch each other. And these are photons, atom-sized computing. So that's the problem. Light is massless, and superconducting supercomputers have mass. You see the great big monster box for the superconducting supercomputers? They're just to keep that cold, to keep the chip cold, so that the electricity doesn't jump from run to run. All right? So that's why I'm saying that the Chinese are on the right track. They're breaking through that entire size barrier. So, Microsoft, okay, you've got all this stuff in theory. What do you do with it? Well, Microsoft has what's called Azure Quantum. If you want to go out and take a look at it, they have developed a quantum developers kit using what's called Q hash, whatever that's called, programming language and libraries. They've got a kernel for running it on their Jupyter notebooks. They've got APIs for Python and .NET, which includes Sharp, that's what it's called, C#, F#, and VB.NET. Virtual Basic, going and running over in Azure Quantum. And then they have extensions for Visual Studio Code and Visual Studio, the ability to submit, they call it Qiskit, I think, Circ and provider-specific formatted applications to the Azure Quantum service. And it's all public. You can go out and learn Q# right now. Why? Because they want, because it's sort of like, do you remember what happened with the atomic bomb? They had, they said, in theory, we can do this. And so the United States said, well, then we must. Same thing's going on with quantum computing. We can do it, so we must. IBM is investing monstrous sums of money. Google, Microsoft, they're all investing monstrous sums of money. Why? Because their asymmetric cryptographic methods are about to be rendered useless. Okay, so they're trying to write for what do we do after that? Okay, so last slide, because we're out of time. Last slide. What does it all mean? Well, these are my thoughts. We can expect the traditional two-key methods, this is one of them, will undergo complete transformation in the next few years. Everything that we've done prior will no longer be considered sufficient. Okay? So it's all got to change. Network encryption, network browsing, electronic signatures, and cryptocurrency must also change in order to remain viable. Is it impossible? No. Is it going to be disruptive? Yes. Is it going to cost a lot of money? Yes. Do you want to keep your crypto secret or not? Your choice. Anybody who chooses to ignore this, they're going to become, like an obsolete shoe factory or something. I remember Jumanji, they had that shoe factory. So, any thoughts, any ideas, any conversation on this? Was this helpful?
Yeah.
Yeah, this was really good, very helpful.
Yeah, in the end, we sort of have to pay attention to this. We're learning how to use cryptography, and today you can still go take this, and like it says, this is coming. Quantum is coming, so you don't have to know about it. But you know what? The 701 study guide, 701 Security Plus, will definitely have it, and the 801 will, blow away the 701. So why not be there on the path already when the other folks, that you sit with and work with start learning? You're going to go sit in a job and somebody's going to say, hey, we all have to go to Q# classes. You say, oh, I already know Q#. What? Well, then you're going to teach the Q# class. Guess what? You become the most valuable kid in the room. And you know more than your bosses. This is where it's going. And we can't ignore it. So anyway, fun stuff. Hope you all had fun with this one. It was a real hoot to put together because it showed me stuff that even I didn't know. Okay. Oh, I see something in chat. Oh, yeah, you got to go. Oh, you're staying. You got to go? You're staying. Gotcha.
Change of plans.
Yeah. Fine. Appreciate it.
I found a article about the minimum Aes strength. Mm-hmm. It can be down as low as 80, but you have to do some risk mitigation. I'm doing a too long don't read version. Mm-hmm. But the 256 is highly suggested.
Right.
Mm-hmm.
Right. I believe that AES 256 was DOD's standard.
Gotcha. So it's an agency by agency. Okay.
Yeah. And by the way, that was 15 years ago. Anyway. All right, guys. Thank you for participating. This has been fun. And if you have any other thoughts or ideas for something to do, a topic for us to cover, please let us know. I love bringing this stuff, and I also want to bring it in a manner that people understand. Again, this was gee whiz stuff, but they have physicists that are still struggling with it, but we've got to learn it. We're going to be dealing with it within a few short years. So let's get smart.
And the building blocks for it is in the Security Plus. So
yeah.
Good to know.
Yep. Okay. Thanks, guys. Have a great Saturday.
Bye.
Thank you.